I think we'll go ahead and just get started here. Let's see. Okay. So today's lab is actually just kind of somewhat straightforward. It's a bit of calculation. You're really just going to fill out these. You're going to do the same calculation like three times each for each calculation. And there's like two different ones. You're just going to fill out these charts, and then you're going to do a pretty simple operation where you just add up the two columns, and you have your third column with the total. And it's going to ask you if any of those values were conserved. And so you'll see what I mean. I'll pull that up and I'll show you what I mean on there. But the main thing to take away from today is conservation of momentum, and I want to show you how to solve a conservation of momentum problem, like the certain setup that I like to kind of show all my students. So we'll go ahead and get started with that. So conservation of momentum is pretty important. I mentioned earlier that momentum is always conserved, but not energy. So we'll see. I'll just put that on here. Energy not always conserved. Usually that means you're going to lose energy to like collisions, heat, and sound, things like that. When you drop a bouncy ball on the ground, you hear it actually hit the ground and bounce back up. You hear that, which means that you're losing energy to the environment. You're losing energy of the actual rebound, and it's going into heat of the ball compressing, and it's going into the sound that's actually being produced. So energy is not always conserved. It can be lost to sound or heat, etc. But momentum, on the other hand, is always okay. So momentum is always conserved. Energy can be lost. Energy can be lost in a collision due to sound and heat and things like that. But momentum is always conserved. Okay. So how do we actually handle a conservation of momentum problem? So here we go. So here's kind of like the setup I want you to think about when you're doing a conservation of momentum problem. Usually you have some initial. Okay, maybe I can make this a little cleaner. You have some initial condition. Maybe not condition is a word, but you have some initial configuration, let's just say, of the system. What that actually means is you have some things moving at some velocity. We'll go over that in a second, but some initial config. Okay, then you have. I draw my dotted line. That's like my collision, or it's like when the magic happens. That's my magic line. Okay, so that's just like where stuff happens, and this is going to be your final configuration. Okay, and you just want to what you're going to want to do is you're going to want to take notes of what. Let's see. Start on the next page here. So, let's see. Simple problem would be just some block, let's say, skating down some surface, moving towards another block that's just sitting there stationary. Okay, this thing has some mass m1. This has mass m2. This has velocity v1, and this thing has velocity v2, but it's 0, right? So this thing here, I'm going to say it's actually moving with some velocity, and then the second block I'm going to say is velocity is 0. V2 equals 0. So it's just stationary, right? And this is greater than 0. Okay, I'm not giving it values right now, but I just want to say there's two blocks. They have some masses, they have some velocities, and they're just one's moving towards the other. Okay, this is the initial condition, the initial configuration. This is, so it's kind of like it's separated by time, right? This is before, and this here represents the collision, and then this is after. We'll go ahead and look at the situation where they stick together. Okay. So you always want to separate your collision problem, which is usually what a momentum conservation problem is, into like your before and your final, your before and after. And then we just kind of, so here's what we do. So momentum itself is an expression is just mass times velocity. So here we'd have some momentum initial. So we look at the total momentum of this first frame, and then we have some momentum final. Okay, momentum is usually represented with the letter P in physics, and it's P equals your mass times your velocity. Okay. So what we want to do is we want to find the total momentum of the system before this collision happens and the total momentum of the system after the collision happens. Okay. So in this case, you'd have P initial would be, let's see. So momentum is mass times velocity. So I just want every mass times its velocity all added up. So I would have m1 v1 plus m2 v2. Okay, and I know v2 is going to be 0, but I'm just kind of being thorough here. Then you have your P final. That would then be, let's see, what do we have? We have two masses stuck together, and they're moving together, right? So then I would say it's a mass of m1 plus m2, and it's moving at some velocity vf. Okay? So it's really just all about adding up all of your little, like, your bodies of certain mass times the velocities that those bodies have. So here you have, m1 times v1, that's one object moving at some speed plus another object here moving at some other velocity, right? And in this final position here, you have one object. So I did the combined masses of m1 and m2 times some vf. Okay. So that's kind of like the setup. I know I'm kind of stumbling through a little bit. Let's see. So yeah, initial final. We have our momentum set up. What we want to do now is we want to say, well, momentum before equals the momentum after. Which means that your P initial, which is the total momentum of the first frame, should equal P final. Okay, so that means my m1 v1 plus m2 v2 should equal m1 plus m2 times some final velocity. Okay. Once again, what that means is I had some initial frame here. So this is like frame 1. This is frame 2. What I mean by that, it's kind of like, it's the before and after. It's the time frame before the collision and the time frame after the collision. What you do is you add up all the little momentums you have in the first frame and all the momentums you have in the second frame, and then get some expression for your total momentum in the initial and the final frames, and then set them equal. And that's always the case. You always want to have some kind of problem like that. So let's see. Yeah, so you'd have, you'd set your initial total momentum to your final total momentum, and you have this expression here. and then you can solve for whatever you're looking for. So in this case, it turns out that v2 is equal to 0. So then I can get rid of this. So I'd have m1 v1 equals the sum of the masses times some final velocity. And let's say I was trying to find the final velocity. Like, let's say I knew the masses of the objects and I knew how fast the one object was flying towards the second, right? Let's say I know what v1 is. Okay. Then I can actually go ahead and calculate what my final velocity would be, assuming they stick together. Okay. So it would be m1 v1 over the sum of the masses. That would be equal to my final velocity, right? So that's just one example of something you could do with a momentum conservation problem. But let's see. So I could do one more. This type of problem here, though, where they stuck together. See, they stuck. Mass M1 and M2, they stuck together. Okay, so when the masses stick, something had to happen for these masses to stick together. There had to be some kind of deformation, so this thing would stick. It would, like, it would. In the example of the carts, we actually use Velcro, so you have like these Velcros like pushing against each other and then like hooking into each other. So it kind of simulates this. But when the masses stick after collision, we call it a inelastic collision. Okay, and that's what I just looked at here. This problem, this little momentum problem that I just kind of made up and sketched out here, is really just, it's an inelastic collision problem because you have these two objects in the beginning, M1 and M2, and after this collision they somehow stick together and they travel together, right? So that right there is an inelastic collision. I imagine like an inelastic collision is kind of like a spitball hitting the wall, right? It goes, it's like there's the wall, it goes, right, just squishes on there. It's a sticky thing. Otherwise, you have something called inelastic collision and elastic collision, and that's where they bounce, right? Which is they can be more complicated. It depends on what they give you, like what kind of values you're given in the problem. But an elastic collision could be more complicated, depending. So that's the thing. Let's go ahead and inelastic collision. Here's the thing: kinetic energy, or I should just say energy, I guess, just to make it clear. But it's going to be kinetic that we're talking about. But in an elastic collision, you have energy is not. Oops, energy is not conserved. Okay, that's because the deformation that's required for this thing to stick is going to naturally produce extra heat and sound. If you have something perfectly balanced, it's possible that it doesn't produce this heat and sound. Like in the lab, we would have the carts that have the Velcros, right? So there's the Velcro pointing at each other, and they would stick. Okay. The other version of the in the lab, the other version of the collision that we experiment with is where we have the magnetic bumpers pointing at each other, and they'll just come like, ooh, they won't even hear anything, right? They'll come up and they'll push each other away like that. So in that situation, we have no sound, and you kind of expect, okay, well then if there's no sound, maybe they're not losing energy, and that would be correct, right? In this situation, we are losing energy due to sound and heat, because of the fact that it's sticky, right? Okay, So in an inelastic collision, energy is not conserved. An inelastic collision is where the two stick together. Masses stick after the collision. We call it inelastic, and in that case, energy is not conserved. Okay, so I'm kind of wrapping that up into like a nice little bow. The other form of collisions we can have is elastic collision. Something like, let's say, have some cart or some block flying at some other block. Right? And then the collision happens. This is like, that's the before, and then here's the after. So here's before. Right at that, but why not? And then, let's see, afterwards, let's go ahead and assume that they bounce off of each other. You can see already why these are going to be more complicated. I've got a lot more variables here. But I can have some blocks heading towards each other, and then they bounce off each other and head back in the opposite directions, right? So how would I handle this? Well, same as before, right? I want to have my total initial momentum, and I want to find out what my total final momentum is. My initial momentum is going to be m1v1 plus m2v2, right? My final momentum would also be m1v1 plus m2v2, okay? Now you might wonder, like, well, one of my velocities is pointing to the left. Yeah. If you're having problems finding the lab, it should be under course documents in the very bottom list. I find the PDF one is the best. Just, I don't have to, unless you want to type inside of there. That's right. Anyway, so final momentum and initial momentum, there they are. It's just really just mass velocity plus mass velocity plus mass velocity for every object you have in the system. Now you might be wondering, how do I deal with these positive and negative velocities, right? Because I have some velocity pointing to the right and some velocity pointing to the left. I would then, see how to take care of signs. You just want to declare a positive and negative direction. So what I mean by that is I would say that up, there's no up as a one-dimensional problem, but I'd say up and right are positive, right? And then down and left are negative. Just as like a standard, I could just go ahead and just say, that's what I'm doing in this problem. That would then mean that when I do substitute my value in for V2, right? You see my V2 here? Let's say I do have some value for that. I would say that V2 is negative, okay? Same with V1 final. V1 final would also be negative. Okay? Now, I didn't incorporate that negative into the momentum expressions here. I did not put that negative here. Okay? Now, the reason why is because you never really know whether that extra term M2V2 or that term M1V1 is going to be positive or negative until you actually enter in the velocity. The reason why you want to do it like that is because your final velocity, your final momentum section over here, you don't know what direction things are going, right? It could be that, like, let's see, if you have a big truck and a small car, and the car's traveling a little faster, but the truck's a bunch heavier and it's traveling slower. Who's gonna win, right? When they smash into each other, are they gonna stay still? Is the car gonna push the truck back, or is the truck gonna push the car this way, right? You don't know necessarily. It seems like the truck would win, but the car's going faster, right? So it has more of an oomph. That would then be, it has more momentum. But the truck's also heavier, and then momentum is mass times velocity. So the truck could have more momentum. You don't know. So you don't know what direction the ball of twisted steel is going to, travel. Let's assume that it was on a track and there's nobody in the car, okay, or the truck. You don't know which direction it's going to go. So you don't know which direction it's going to slide after. So you have to actually let the math tell you that. And I was thinking maybe I'll do one of those examples and then I kind of let you get started. Because the whole lab is basically just finding your total momentum. Really, though, I wouldn't get too lost with the setup of the lab. What you have is you have three different situations. You have part A, B, and C, where you have carts with the same mass and carts with different masses, and you have the elastic collision, you have the inelastic collision. So one of them are going to stick, and the other ones are going to bounce. And that's really just because we have the magnetic bumpers facing each other, so they bounce off, or you have the Velcro facing each other and they stick, right? But you're really just gonna you're gonna be given masses and velocities, and you're just gonna ask it's pretty simple. I'll pull it up in a second here. As far as solving one of these momentum problems, let's say that we have I don't know. I didn't bring my calculator out here. I'll grab one in a second. Let's see. Okay, so you have okay. Again, let's just assume that they're on a track or something. Nobody gets hurt. Okay, cool. All right, so let's say we have a truck and a car head-on collision. Let's go ahead and look at the before and after. Right, the beforehand is they're heading towards each other. Afterward is they've collided and become one ball of something. Right. I'll go ahead and give these things values. Let's say that. Oh shoot! Let me use my calculator really quick. Okay, well, of course, naturally, it's not right there where I thought it was, so that's great. So, let's just say the car is M1, and let's say that it has 2,000 kilograms. Okay, and let's say the truck is M2, and let's say that's 4,000 kilograms. And the car's initial velocity. Let's say okay. Okay, so let's say its initial velocity is negative 20, and let's say the truck's initial velocity is 10. No, let's not make it 10. So the truck's initial velocity is 15. Okay. Should be kind of obvious what's going to happen here, I guess. Well, if you knew what the math was going to be, but whatever. Let's just go ahead and calculate it. So, head-on collision. I said that my car has a negative velocity, but the problem would actually give you, they're heading towards each other, and it would just tell you that one's 20 meters per second, the other one's 15, right? It wouldn't tell you this negative. I'm going to go ahead and say it's negative because of where I'm going to draw it. Yeah, so whatever, I'll do that. So, I'm not going to draw a truck in the car, I'm just going to draw blocks because, that's what we do. So, let's see. Here's my mass, let's make that mass 2. Heading to the right at some velocity v2, and here's my car. Heading to the left. Okay, that's before. And afterwards, they stick together, right? Twisted, mangled metal. They stick together, okay? So we have mass 1, mass 2. They're stuck together, so that's going to be one object with the combined mass. But where is the final velocity, right? Is it left or right? Is it going, is it pointing this way? Is it pointing this way? I don't know, right? Don't actually know. So this is why I keep the negatives inside of my velocities, okay? Because it's going to be able to tell me something about the problem. Now what that means is, I can go ahead and draw the arrow somewhere if I wanted to, but it's got some final velocity, okay? So my P initial, is going to be M2 V2 plus M1 V1, right? Just adding up the individual momentums. P final is going to be this total M1 plus M2, because it's one object with the total mass, times some final velocity. Okay? So, again, just like before, that's what we're doing here. I'm going to solve this for final velocity because I want to figure out whether it's going left or right. Right? So here we go. So I'm going to have these two equal each other. P initial equals P final. And I have M2 V2 plus M1 V1 equals M1 plus M2 V final. Now, why am I showing you this, by the way? Just kind of step back out of it for a second. This is kind of more important than just showing you the procedure for the lab. The procedure for the lab is basically just, it's a little more simple than this, but this is kind of how you solve these kind of problems, so I just want to show you that because it's more useful to know. Okay? This is like the takeaway from the lab, and then the lab itself is just, somewhat diminished in value since it's all online anyway. So, okay. I want to find my final velocity, so I'm going to divide that sum over. So I have M2 V2 plus M1 V1 all over M1 plus M2, and that's going to equal V final. Okay. Note that if V final is greater than 0, that's to the right, and if V final is less than 0, that's left. Okay, because I've declared earlier on, and here I can declare it again, that right is positive and up is positive. Oops, it's pretty hard to see. Yeah, I'm declaring that to the right is positive and up is positive. Okay. So that's the thing. I'm going to actually plug in all my values, and if I get a negative for V final, then I know it's moving to the left. The car won. And if it's positive, it's moving to the right, then that means the truck won. So I go ahead and enter my values, and this is where my negative would come in. So I have, let's see, M2 V2. That's 4,000. I'll leave the units out. 4,000 times 15 plus, and I have 2,000. Times negative 20, right? All over the 4,000 plus the 2,000. That's going to equal my final velocity. So we have this. Let me go ahead and add this up here. Okay, so turns out I got 3.333. All right, so I got a positive value of 3.33 meters per second as my final velocity. Okay, so what does that actually mean? Well, because I decided to call leftward motion negative, right? That's what this v1 being negative 20 means. It to the left means a negative velocity, and the right means positive velocity. That means that because this final velocity here is positive, that I know that it must have been this direction. It must be that the truck won, right? So these things are heading at each other, and then the truck just won a little bit and pushed the car further to the right. Okay? This is just me showing you why I make a big deal about the sign thing. Don't put the sign inside of your momentum, right? Final momentum over here, I didn't say that it was negative. I didn't say it's negative m1 plus m2 times VF. I didn't say it was negative because I don't know whether it was going to the left or the right. I just know that the value of it is going to be the total mass times velocity. So just keep it as like mv plus mv plus mv, or whatever it is for however many objects you have. But just make the velocities negative if they're heading to the left and positive if they're heading to the right, and then put that into your expression like this with the negative right there. And that'll tell you, when you get a final velocity, if it's positive, you'll know, oh, that means it went to the right. If I put a negative in my final momentum term, this m1 plus m2 times vf, if I put a negative here, then I wouldn't really know what the hell my positive final velocity meant. I wouldn't know that actually means it's going to the right. So that's why I make a big deal about this. But okay, so that's kind of like the background. That's how to solve these kind of problems. I'll give you like another quiz, at some point soon here, and this will be like a problems on there. But again, I'll give you like, a practice quiz with the things solved out, and then I'll just have you do another one that's very similar to it. Although on the last quiz, I didn't intend for it to be a quadratic that you had to solve. I didn't realize I actually gave you that to do. So, but with all the resources online and everything, you all figured it out, so that's good. And some of you remembered your quadratic formulas and stuff. Okay, so what I'm gonna do next here is I kind of want to like just go over the lab, what exactly you're supposed to do. So I'm gonna switch gears now. Let's see. Okay, so here's the actual lab that we're doing. Now you can see here, go back up to the top, we need to start just filling things right here after the data section starts. It's pretty straightforward. So, okay, so you can see right here, we're given the velocities and we're given the masses of the carts, right? So the sum here is just literally just adding up. Okay, hold on a second. This sum right here is just adding up the row, the rows to the left right there. So you add up this and this to get this final row here. Okay. So that's literally all you're doing with the sum of 1 plus 2. It's just adding up the two spaces to the left. Okay. That's so that you can get a total velocity in the first frame and a total velocity in the second frame. This is how we're going to be able to like see whether or not something's conserved. You can see that we're going to have total momentum and kinetic energy too. How do I find momentum? Well, in this first block here, right? What's it going to be? Well, it's the first cart's mass. That's m1, right? Which is up here. It's 0.732, right? That's the mass, and then the velocity you're actually given right there, 0.258, right? So you have this mass times that velocity. I wish I would stop doing that. Okay, that top velocity there, and that's going to be what this momentum is here, right? Does that kind of make sense? So you have 0.258 times the 0.2732. That's going to be the momentum of P1, or P initial, okay? I wish this thing would actually, Jesus, if I do that. Because there's that number, that's the mass of the cart, and that right there is the velocity of the cart, of cart 1, right? Cart 1's initial velocity is 0.258, and so then its initial momentum is just it's just those two multiplied, and that's going to be in this box here. Okay? That box there. No, she just doesn't want to do it, does it? Okay. That kind of makes sense. You're just going to do that. Also, kinetic energy. Kinetic energy is 1/2 mass times the velocity squared. Right, so don't forget to square it. Okay, so that's going to be the same thing. You have the masses of the carts, you have their velocities, so you can go ahead and find the momentums and the kinetic energies and just fill them into these boxes. Okay, so you can see that this box right here, right there, that's P final for cart 2. So then you would have mass 2 times velocity. You'd have times this velocity here. Shit, not that one. This one. Yeah. Okay. Yeah. Some you're just gonna add the Okay, and it's gonna be the same thing for all these actually. So it's just really you're just gonna be filling out this data stuff for a minute. Okay. Again, here use your masses, velocities, multiply the two to get momentums, and then 1/2 mass velocity squared gives you the kinetic energy. Okay. So you just do that 3 different times here, right? And then it's going to basically just ask you, is it conserved? I'll be right back. Okay. Sorry about that. So let's see. How you guys doing? So hopefully the filling out of these tables here is somewhat straightforward. Like I said, you're basically just okay. I don't know how else to explain this, and this stupid thing won't quite do what I want it to. I draw there. So this box, that's going to be this value. Ugh, God, why does it do that? Holy hell. Okay, cart 1, P initial, that's going to be your, P is equal to, you have M1 times VI1, essentially, okay? VI1 is cart 1 and it's VI, so it's 0.121, right? This right here is your velocity of the cart 1 in the initial frame, and then you have your mass, and you multiply the two, and that's how you get your momentum down there, right? And you just do that for cart 1 initial, cart 1 final, cart 2 initial, cart 2 final. Then you also find the kinetic energy for cart 1 initial, final, cart 2 initial, final, and just put all of those values in there. Okay, so it's really just MV, 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 and then MV squared divided by 2, MV squared divided by 2, MV squared divided by 2. Okay, for the is it conserved chart at the end, do we take into account possible experimental error? Total initial intelligence, we're off by. Table 1.3. Right. They're off by 0.003. If it's that close, I'd say it's conserved. Within some error, there's always going to be a little bit of error, but if the numbers are very, very close, and then you notice a pattern where they're consistently close, then you would then say that it's conserved, right? You don't really know if it's a pattern yet because you're just looking at one data point essentially, but yeah, they're basically conserved. Where the hell is my calculator? Well, yeah, so to short answer, Nicholas, I'd say that's conserved. If it's off by 0.003 or 0.0003 or whatever, that's close enough. And in fact, for momentum, you should always expect that it's going to be conserved. So if it's off a little bit, just go ahead and just say it's conserved. But for momentum, it will be. For the velocities and the kinetic energies, not so much, but definitely the momentum. That was horrifying. There's some big beetle crawling across the ground next to my feet. My velocities are the same. So do I say it's conserved? You mean the sum? If you mean the sum of your velocities are the same, like this, like these boxes here are the same, then yes, you would say they're conserved. Velocity conservation is not something that's a thing. No. Okay, it's not showing the interpreters now. Yeah, so velocity conservation is not a thing. But here, it's just an extra value that they're trying to see if you can, if it is conserved. It's not something that we actually do in physics. We don't really look to see if velocity is conserved at all. We just look for momentum and kinetic energy. Well, not just energy in general. I hazard to say in this form, yes. In what we're doing, yes, it's going to be kinetic energy only because we're not talking about potentials here. But I find it hard to just say kinetic energy. Well, let's see. Looks like yes. Yeah, if your velocity is negative, then your momentum would also be negative because it would just be mass times that negative velocity. Your momentum is also a vector, so it also has like a directional component. So you'll have some value at some, either it's positive or negative, depending on, if it's just one dimensional, then it's negative means left and positive means right. But, if it's multidimensional, then you actually have to you treat it like a vector where it has components in the x and the y direction. Now, as far as the velocities being conserved, I actually haven't checked this myself, but 0.192, 258. So, like, the first one, it is conserved inelastic. It looks like the other two are not. So, yeah. Don't get too hung up on the velocity conservation thing. I think it's kind of a silly question to ask. It's just on there. I could have even told you not to even fill that one out, but it's just, I don't know. Okay, question 1. You're down in this section here. Yeah, is it conserved stuff? Pretty straightforward. Let's see. Okay. In section 2A, final velocity of the first cart is 0. Cart 1 should come to a rest. Did your cart do this? If not, what's the reason why it may or may not have been perfectly at rest? Okay, 2A, final velocity. 2A. Okay. Cart 1's final velocity. Okay, so right here, cart 1's final velocity is actually negative 0.002, right? So it's almost perfect. Not quite, though, right? So you can see it's trying to be 0, for lack of a better term. It's trying to be 0. It should be 0. It's not. Okay, so the answer then is, let's see. Should come to rest. Did the cart do this? Not exactly, right? It almost did. It was moving a little bit, so it didn't quite come to a rest. What's the reason why it might not have perfectly come to rest? Let's think about that one. So after the collision, the thing continues to move. Why would that be? There's a couple different reasons. One is the track could be at an angle. Okay, there could be some slight angle to your track so that after the collision happens, this thing should be stationary, but it actually starts to fall down the track because of gravity, right? So it could be that through human error, your track is not perfect. You used a level, but like it kind of got thrown off a little bit, right? So there's one reason. Another one is the carts aren't exactly the same mass, right? Like you could have some variation that it's like not even measurable or didn't show up or what it might be. Let's see, section 2 here. The masses are, check it out. So these masses are a little different, right? There's 0.2712 and 0.2732. They're off just by a little bit. So small, it's almost immeasurable. But you can see that, if you actually did the momentum conservation, what would happen here? It's kind of like the last lab we did, where you'd have all the momentum transferred from one cart to the other. Here, that was the case with the carts with the same mass, right? If they weren't the same mass, then it might not all transfer like that. The first cart coming at the stationary cart wouldn't just stop while the second cart continues if their masses aren't equal, right? If the masses aren't equal, then you could have something like this where this hits this one and then continues going. Or it could come and hit this one and kind of bounce off while this one goes this way, right? So if the masses had to be perfectly equal for that perfect exchange where one's moving, one's stationary, and then they trade places. They have to have exactly the same masses for that. Here you can see they're off by a little bit. 0.2712, 0.2732. So that right there is the main reason. Just looking, the whole cart, the whole track thing being off is like a potential problem, but actually now that we're looking at it, the masses are definitely different, which would mean that there would not be a perfect exchange of momentum. There would be, there is an exchange of momentum, but it wouldn't be all of it goes from one cart to the other. You have a little bit left in one of the carts because it was a little heavier or a little lighter than the other one. I might as well look at these other questions too. Why is it important to make certain we're using a level, frictionless surface? Well, level, because you don't want these things to start accelerating, right? So conserved versus not conserved doesn't mean the values are equal if it's conserved. Yes. If the total of something, whether it be momentum, velocity, or energy, before the whole collision and after collision are the same, then it was conserved, right? And how do I know that they're the same? Well, it's these columns right here, these double stack columns here. If the top box and the bottom box are the same number, that means that your total momentum in the initial and your total momentum in the final were the same, and they're conserved, right? Same with your velocity. If the top box is your total velocity in the initial frame and your bottom box is the total velocity in your final frame, if they're the same, then yes, it's conserved. If they're different, right, then you'd have if they're different values, then something was lost somewhere. And you're going to see that that's definitely the case with velocities, and you're going to see that's the case with your kinetic energies, which I also don't want you guys to think about this one too much, because we will talk about energy and stuff. Just do the actual calculation, plug it in there. You'll see the energies aren't conserved in which one here? It should be the inelastic. The elastic one you should have conservation of energy, and the inelastic you should not. So yeah, so these should not be equal. As far as question 2 goes, why is it important to make certain we're using a level friction on the surface? Level because you don't want that car to start accelerating down the track, right? You want to give it some initial velocity, and you want to stay at that velocity. But if it's accelerating because it's at an angle, that's going to throw off all your numbers, right? So that's why you need a level surface. Friction on the surface is the same thing. It's if the cart's experiencing friction as it rolls down the track, it's going to slow down, right? So your velocity is going to change because there's a force being applied to it. Both those things boil down to we don't want any forces applied to these carts that isn't a collision, right? Well, the only forces in this problem to be, or in this lab to be the forces due to the collisions between the carts. We don't want there to be a force on the cart accelerating it down the track because of gravity. So we don't want a force of gravity thing. We also don't want a force of friction because that would also change the velocities of the carts. So that's number 2. We don't want any extra forces in there. And that's why friction, avoid forces, and level, avoid gravitational forces. In section 1, some of the kinetic energy is lost after collision. Where did the energy go? And that's what I mentioned earlier. Kinetic energy is lost in collisions to sound, heat of the compression of the material. Those are the 2 big ones. Compression, the material kind of tells you friction. So it's friction and sound, right? And don't worry about this additional reading stuff for now. You could if you want to, but yeah, this lab, if you boil it down, it's really just I want you guys to see what momentum conservation is, how to solve some of the problems, and I put those into the notes, and you can look at those later, and I'll also put that on a quiz, so you actually have to do it. The rest of this is kind of just, filling out the data and answering just 3 questions, so it's pretty straightforward. Disregarded. Yeah. Don't worry about any stuff that we may have missed or whatever. There's actually a couple labs that are just kind of busy work, so it works out that we can just disregard a couple. Yeah. So just worry about the ones that we actually met for. Don't worry about, those last 2. This is the next one that we would have done anyway. There's some other one that's Archimedes principle, and it's kind of ridiculous. Especially online, so I'm going to throw that one out. Question 3. Some of the kinetic energy lost in the collision, where did the energy go? Yeah, I think we only have 2 labs left as well. I actually have to have to check when the grades are due and all the other stuff. Didn't squeeze 5 quizzes into this, so oh well. I'll just leave it at probably just 2 or something. Maybe I'll give you 1 more after that. Maybe I'll squeeze 2 more quizzes in and have it 3 total or something. I don't know. But yeah, we're getting pretty close. Okay, question 3. Where'd the energy go? In the kinetic energy was definitely not conserved. Where'd the energy go? The energy went into sound. If you actually were there and you'd hear these carts collide, you'd hear a collision. The only way that you can hear collision is if some energy was put into vibration of the atmosphere, which then you picked up with your eardrums, right? With your little hairs in your ear, inner ear, whatever. But energy was lost to heat and sound is the short answer. Question 1. The carts weren't... So the second cart was at negative 0.001 or something like that. The reason why is because the masses weren't perfectly the same. If the masses were perfectly the same, then one thing's motion would trade into the other cart. So the cart would be sitting here, and you have one cart come in, and it would hit that one, and then the cart that was moving originally would stop, and the cart that was originally stopped start moving. And that was what you had in the last lab. In the last lab, you had a perfect exchange of momentum with those charts, with those graphs that like went up and down at the same time, right? In one of those experiments, you had a perfect exchange of momentum where the cart was moving, the one was stationary, it hit the stationary one started moving, and the one that was moving stopped. That would be if the carts were the same mass. But if you look at 2A, if you look at the masses, one's a little bigger. You can see one's 0.2732 and the other one's 0.2712. So because the masses are a little different, it doesn't perfectly just exchange its velocity to the next card over. Submission link. I may have forgotten to do that. Let me stop my share. All right. You should now see a submission area. Okay, I think pretty much gone over most of the stuff. I think I might stop the recording now.